Welcome back to Vibrations. This is week one, and this is video 4. All right, so we often will call the natural frequency of something the omega n, and it's the square root of k over m. But this is in radians per second, and we refer to it as the circular natural frequency. Well, we can think of that motion, we can imagine the motion up and down as kind of being related to this sort of circular diagram where we're rotating around and we're oscillating back and forth and back and forth. With the angle that we're using, especially since that we will have a solution that is of the form, and I'm just going to make this generalized. Sometimes we use capital X, and then this sign of omega nt, and I'm not going to bother putting a phase in there. Although I could show you right here, it has a phase of angle of 0 here at the beginning, right? If it had a phase, that would be like it would be starting at a different spot on a sine wave, but this is accurately portraying this right here. And I should also mention that this graph is omega t, right? So it's assuming that the period is 2 pi times t, right? So we don't quite, it's not normalized for that. And then, well, I should have put in the amplitude right here. They did write the amplitude in this graph, so A, right? But anyway, wanted to point this out right here. I'm not sure Dr. Bob actually uses this page out of the book, but I thought it was important right here. That you could transform from this time domain. Do I want to call it time domain? Maybe. Right here. Yeah, I don't know. I guess go from sines and cosines, which is being described up here, down to the imaginary and real. So this often will be the real axis. X will be treated as real, and this will be the IMG, the imaginary axis. And what we're able to do is using the Euler identity, or equation, depending on who you ask, identity, I think that's right. The Euler identity, which is e to the I theta, is equal to cosine of theta plus I sine of theta. Essentially, what we've done here is we're going from polar coordinates into a Cartesian coordinates, essentially, because the real part of this is the x, and the imaginary part is the y. So we've taken this guy and really kind of made this possible, right? So, for instance, if you took z is equal to a e I omega t, and you substituted the Euler identity into, for this right here, we would find z is equal to a times cosine of theta, well, no, excuse me, theta here being omega t, and I didn't say omega n because we're not necessarily natural frequency, plus I, no, do I want to put I there? Sure. A times the sine of omega t, right? So that's just the process, just to go from there to there, and that's all there is to it. This is the real coordinate. That's this coordinate right here, and this is the imaginary coordinate right here, right? So we have established x's and y's by going back and forth between those two. It's useful for simplifying some derivations, but it's also the language of vibration. Often we'll jump back and forth between using cosines and sines and using the e with the imaginary number up in the top. All right, so here's the position, the velocity, and the acceleration as functions of time, and we'll note that since in the most basic of cases we have x is equal to a times the sine of omega t, if you take the derivative of it, you get x dot is equal to a omega cosine of omega t. And as they've shown right here, they're going to be 90 degrees out of phase. So here is like the peak of this. That's also 0 here for that. And there's the peak of that. That's a 0 for there. And so forth. There's the 0 for right there. There's a peak for the 0 right there. You get the idea. So what they're saying is the magnitude of that is just going to be omega A. And then if you take the second derivative of that, it's going to be negative now, but it's going to be A omega squared times the sine of omega t. And that is going to be 90 degrees out of phase with the velocity, but 180 degrees out of phase with the position. So you'll see that here's that spot, and here's that spot, and here's that spot, and here's this spot, and they're out of phase with each other. Now I said insert page 4.5, in which we explore some more of this. So I'm going to go ahead and wrap this video up. I'm not sure if that was a great video, but it is a video. So this is video 4, I think. And I'll move on to